is very hard. Need to calculate the, so it says a single phase motor is fed with a cable, 240 volts, and it supplies 4 amperes. And there's a capacitor connected here, but you are given this current and voltage. So first part is to find the apparent power supplied by the source. So that's really hard. You need to multiply these two numbers. 240 into 4 gives you the apparent power supplied by the source. So that's 960. That's a waste of a page. And then part B, it says the motor consumes 750 watt at lagging power factor of 0.8. The cable consumes 100 watt and 50 volt ampere reactive power. Calculate the combined real and reactive power of the cable and the motor load. So this motor consumes 750 watt, and this cable consumes 100 watt and 50 volt ampere reactive. So the total real and reactive power consumed by these two will be the sum of the real and reactive power of individual elements. So we need to figure out the reactive power of the motor. So you are given the power factor and real power. So apparent power will be 750 divided by power factor. So that gives you 750 divided by 0.8. So the apparent power for the motor will be 937.5 volt amperes. That's the apparent power. So we have the motor apparent power, that value, and the real power is given as 750. The reactive power will be this apparent power squared minus real power squared square root. So that will be 937.5 squared minus 750 squared square root gives you the apparent power, sorry, reactive power. So that turns out to be 562.5 volt ampere reactive. So now we add everything up. So real power 750 plus 100 gives you the total real power, which is 850. And the reactive power, you have 50 here and 562.5 there. That gives you 612.5 volt ampere reactive. So that's the total real and reactive power. So next part, determine the power factor seen by the source and the total reactive power delivered by the supply. So we calculated the reactive power quantity here, so that includes all the this total, including the capacitor. So if you consider the elements that consume real power, you have the cable copper losses and the motor real power 750. This doesn't have any real power consumption. So the total real power will be the same as this. So P total is 850 watt. The capacitor doesn't consume any real power. The apparent power total is this particular value which we calculated. That's the supplied apparent power. So the power factor is the real power divided by apparent power. That's the power factor. That's 850 divided by 960. So that turns out to be 0.8854. That's the power factor. And then we have to figure out the reactive power supplied by the source. So you have the real power, apparent power, and then reactive power supplied will be S squared minus P squared square root of this. So that's 960 squared minus 850 squared. Square root of that turns out to be 4 6.2. That's 6.2 volt ampere reactive. So part D is to determine the reactive power supplied by the capacitor. So we have this much of reactive power supplied by the source, but the motor and the cable consumes this much of reactive power. So the remainder it's actually compensated by the capacitor. So we can write the reactive power Q total is the sum of the motor plus the cable plus the capacitor. This is the total reactive power. So these two, we figured that out. That's 612.5, and the total reactive power supplied is the 446.2. So the capacitor reactive power is a negative value. So that's 446.2 minus 612.4. 166.3 volt ampere reactive. This is the amount of reactive power supplied by the capacitor. So if you consider the capacitor reactive power, we can write Q equals V squared over XC. That's the reactive power, the voltage across the capacitor squared divided by the reactance of the capacitor. So XC turns out to be 1 over omega C, so we can write this as V squared omega C as well. So then the capacitance value will be this magnitude of this divided by V squared omega. So this is basically the magnitude of reactive power supplied by the capacitor. So we have 166.3 here, and then V squared is 240 squared 2 pi f. So that's 2 pi 50 here. Gives you the value of capacitance. And last part of that, draw a phasor diagram clearly showing the voltage, source voltage, cable current, and the voltage drop across the cable and the load voltage. So here we need to draw the phasor diagram representing this load voltage, voltage drop across the cable, and the load voltage. So the load voltage, that's the motor voltage, and there's a voltage drop across the cable, and this is the supply voltage. So we can draw the motor voltage as our reference. That's, let's say, VCD. That's the motor voltage, and there's a motor current that's lagging by a certain phase angle, and the cable, the cable includes some resistance and reactance, so you can draw some voltage drop across the resistance and the voltage drop across the reactance that's perpendicular to this. This phasor is the voltage drop across the resistance that's parallel to the current. This is I and cable current, and this is IR cable, and this is IX for the cable, and the effective supply voltage will be somewhere here. This is the source voltage. So this is basically for a lagging power factor. If you have a leading power factor, it shifts to the other side. Any questions on that? So second question, have a three-phase circuit, says a balanced 10 kVA three-phase delta connected load, that's this load, has identical elements, so these are three identical elements, and is energized from a 415 volt line to line 50 hertz AC supply with ABC phase sequence. It is found that the three-phase delta connected load consumes a total of 700 watt real power at lagging power factor. So this is, so you are given the volt ampere and the kilowatt values of this particular load. This consumes P, you are given 7,000 watt, and the apparent power consumed in this element is 10,000 volt amperes. That's 10 kVA. So we have to figure out the power factor. So that's again real power divided by apparent power. So that's 7,000 over 10,000 gives you 0.7. And then we have to figure out the load current. That's the magnitude of load current, I load. That's the current supplied from the line to the delta terminal, and the delta branch current. So for this particular load, we can write the apparent power equals root 3 V line to line I load. That's the apparent power equation. If you consider just the individual three elements, we can also write this as 3 times V line to line I delta branch current as well. So it's this the apparent power. This is the line-to-line voltage. If you consider just the current into the node of the delta, that's the load current, that's the current coming in here. And if you consider just the branch current, this is the apparent power of one of the elements, and you have 3 such elements, so that's 3 times that. So it's the same. So we want to find out these two values. So basically, I load will be the apparent power divided by root 3 times line-to-line voltage. So apparent power is 10,000 divided by root 3 line-to-line voltage of 415. Which is 13.91 amperes. That's the load current. The branch current, if you can guess from this one, the branch current is I delta. That will be root 3 times higher than the load current. So this one is basically, from this expression, we can write I delta equals 1 over root 3 I load. So that's basically this divided by root 3 gives you 8.03 amperes. Sorry? Yeah, I'm not marking, so Kaz is marking. I can't take the responsibility of it. No, I think if, so it depends. So always you need to show the steps you've taken. So oh, you mean the delta current here? Oh, okay. So this is the branch current. That's the branch means it's one branch inside the delta. Yeah, so you have the line current. So if you have a load, the line current does. Oh, okay, yes, yeah. Yes, yes, yep. For 415, that's the voltage here is energized from a 415 volt line to line AC supply. So that's this particular voltage is 415. Three times. You mean so? If you consider the just a three-phase load, let's say some load, it can be a star or a delta. This is fed by a source which has a line quantity called a line-to-line voltage. That's the voltage between two lines. So this is the line-to-line voltage. So if you consider just a single phase, the per phase value, that's V phase, is the line-to-line voltage divided by √3. Yes, yeah. So moving on to the part B, says a star connected, yep, a star connected capacitor bank is in parallel with the load shown in Q2. Calculate the capacitive reactance needed in each leg of the star to ensure the power factor as seen by the source is unity. Calculate I line 2 feeding the capacitor bank. So we have a capacitor bank here. So that effectively we want this capacitor bank to cancel out the reactive power of this, and you are not providing any reactive power from the supply. So basically the Q source equals the Q, let's say the load plus the Q capacitor bank. So this is negative, this is positive, so these two cancel out each other, and then this becomes 0 when it's a unity power factor. So Q cap has to be the negative of reactive power of this combination. So here the Q is S squared minus P squared square root. So the load consumes this much of reactive power. This is the reactive power consumed by this load. So the capacitor has to provide negative 1.4 this much of reactive power to the system in order to cancel that out. So now if you look at the the reactive power supplied by this star arrangement, the voltage here is the per phase voltage. So we have V per phase voltage squared over XC. This much of reactive power supplied by one capacitor. You have three such capacitors, so it will be 3 times this. This is the total reactive power that has to be supplied by the total 3-phase star connected load bank. So if we factor in √3 here, we can write this as V line to line squared over XC as well. So it's √3 times per phase voltage is line to line voltage. So this gives you XC Q V line to line squared divided by Q cap, the magnitude of that, which is 415 squared divided by 7141.4. Which turns out to be 24.11. So that's the reactance of one capacitor. So we need to find the line current. So if we consider just the capacitor being fed by the per phase voltage, we can write the line current, the second line current to the capacitor is the per phase voltage divided by XC. So that's 415 over root 3 divided by this particular value. So that will be 415 over root 3, that's the per phase voltage, divided by the capacitor reactance. So that's the current through the line current into the capacitor bank. So the last part of that, calculate the load current, I load, that will result if the load elements ZBC and ZCA are removed from the system, leaving only the ZA connected. So you have to see what happens if these two elements are removed from the system, and then you just have this particular impedance across the phases A and B. So the load current and the delta current, the branch current, is the same then. So you have this 415 voltage across that particular element, and that will give you that delta current. So in that case, the new load current, let's say new, will be the delta current from the previous answer, which is 8.03 amperes. So the element impedance doesn't change, the voltage doesn't change, and the current through the element doesn't change as well. Any questions on the three-phase circuits? No. So question 3, transformer question. This is the one you said is hard, is it? The electrical parameters of a 10 kVA 6.6 240 single phase transformer, primary and secondary winding are as follows. So you are given the high voltage side resistance, leakage reactance, low voltage side resistance and leakage reactance. The magnetizing reactance and the core loss resistances are not given. When the transformer secondary is open circuited and the primary is supplied at rated voltage, the transformer consumes 100 watt and has a primary current of 25 milliamperes. So we have the transformer. So this is the high voltage side, 6.6 kilovolt and 240. So this is the secondary, is now open circuited. So let's say you can assume the shunt parameters to be either on the secondary side or the primary side. So let's say, for example, if you assume it's you place it here and the other elements are here as well. So this is open circuited, so there's no current in this path. and this is the high voltage side impedance, let's say R0 high voltage side and the X0 high voltage side. And this consumes 25 milliamperes, and this is at a voltage of 6.6 kilovolt. So this element then consumes the 100 watt. So we can write V squared over R0 equals the open circuit power loss. So R0, this is on the high voltage side, will be V squared over P open circuit power loss. So that's 1600 squared over 100. So that's 435.6 kilo ohm. This is on the high voltage side, but then you are asked to find the impedances on the low voltage side. Oh, sorry. So, so you have the real power. So to find the reactance, we need to figure out the reactive power. So the apparent power for this test, let's say S open circuit, will be the voltage times the current. So that's 6.6 times 10 to the power 3 and 25 milliamperes. That's 10 to the power minus 3. So that's 6.6 times 25 is 165 volt amperes. That's the apparent power. So the reactive power will be apparent power squared minus real power squared square root. So that will be 165 squared minus 100 squared square root gives you the reactive power, which is 131.24 volt ampere reactive. And then you can do this same calculation to find the reactance, the magnetizing reactance. Refer to the high voltage side, V squared over QOC. So that's 6 divided by 131.24. Kilo ohm. These are all, both these quantities are on the high voltage side, but then we want the value from the low voltage side. So we need to transfer everything to the low voltage side. So we need to either multiply or divide by the turns ratio. So here the turns ratio is 6.6 10 to the power 3. That's the primary voltage divided by secondary voltage. So that's 27.5. So when you high voltage side, as I mentioned, we have high impedances. The low voltage side, you have lower impedances and higher currents. So these impedances have to drop when you move to the low voltage side. So effectively you need to divide it by this particular value squared. So here it will be 435.6 over 27.5 squared. Gives you 576 ohm. So this is a kilo ohm quantity. And then here you have 331.9 kilo ohm divided by 27.5 squared. Which is 438.8 ohm. So that's one way you could do this. You could do it in an alternative way. You could initially assume that this is on the, it's already referred to the low voltage side. So if you do that, then you are exciting this at 6.6, and then the corresponding secondary voltage will be 240. So and then you assume 240 on this side and then do the calculation for that particular 240 squared divided by 100, you'll end up with this value. Yes, yeah. Is it a mistake or I shouldn't say a mistake, it's an intelligent decision. So effectively, if you have 6.6 here, this side will be 240 anyway. And then if you move this to the other side, that's you referring it to the low voltage side, and then you can, the real power consumption is, you can assume that's pretty much in this resistor. That's the same if you move it to the high voltage side or the low voltage side, it remains the same, the power consumption, the value changes. So probably that is the easier way to do it, I guess. This one you have multiple steps. So the next part is determine the equivalent circuit parameters of the series branch of the transformer referred to the low voltage side. So now you are given the individual elements. So you have so you are given these individual elements as 75 75 and 25 and 0.05 and 0.18. So we need to move this to the low voltage side. So the turns ratio here is 27.5 to 1 turns ratio. So you need to divide these elements by 27.5 squared. So here you'll have 0.05 plus, when you refer this to the other side, you'll have 25 and 27.5 squared. So when you move to the low voltage side, the impedances reduce. That's the equivalent resistance. So we are going to do this, transfer everything to the secondary side, and this will be your Req and Xeq. And here you'll have 0.18 plus 75 over 27.5 squared. That's the reactance. So we found these two values. And then the part C of that question, the transformer supplies a load of 8 kVA at a rated secondary voltage of 240 at a lagging power factor of 0.8. Calculate the transformer primary voltage under this condition. So we have this transformer. Now we've referred everything into the secondary side. So that's this resistance and reactance. And this, it's feeding a load at 240 volts, and it's 8 kVA at 0.8 power factor. So we need to first figure out this current, let's say I2, and once you have I2, we can figure out the voltage drop across this resistance, the transformer impedance, and figure out this voltage. That's the induced voltage on the secondary, and then the primary referred that voltage. So this one is V1, which will be the transformer terminal voltage. So if we write this, we have the 2, that's 240, that's our terminal voltage on the secondary, plus the voltage drop is the impedance here, which is 0.08305 plus 0.2792. That's the transformer impedance times the load current. So we need to figure out load current. We have the voltage, we have the kVA value. So 8000 divided by 240 gives you the current magnitude, which is 33.33, but has a phase angle. It's a lagging power factor 0.8. So cos inverse 0.8 is 36.87. So that will be 36.87 here. So this whole thing gives you the voltage drop across the transformer impedance. So I'll just write this step as well. That's 9.709, 36.56. That's the voltage drop, plus another 240 here as well. That gives you 247.86, 1.33 volts. That's the V2 value there. So we need to find the primary voltage. So we need to multiply this magnitude by the turns ratio. So that multiplied by turns ratio gives you 247.8 times 27.5 gives you 6814.5 volts primary voltage. So this is probably the more accurate way. You could also, so if you look at this value, this is really small, the phase angle at the terminal voltage and the primary. So you can actually use the equation from the formula sheet, which is so you have this particular formula. That's V1 cos delta. This is a scalar equation. What we did was a phasor addition. So if you use this one, you can assume delta is really small. So if you look at this one, it's 1.33. So cos 1.33 would be close to 0.999 or something like that. So if we were to do that way, it will be V1 or V2 magnitude will be 240 plus the current magnitude, which is 33.33 times R cos phi. So R is 0.08305 0.8 and X sin phi, so that will be 0.2792. Sine would be 0.6. Will give you the voltage, approximate voltage value. So that gives you 247.79. So this expression gives you 247.79. So it's fairly close enough to that value. If you can use either technique to calculate this form of calculation. Either way is fine. This would be more accurate, but then the difference is we neglect the cos delta to be close to 0. But then if you were given the source voltage and asked to calculate the terminal voltage, the load voltage, then you can't use this approach because you don't know delta. Then you need to calculate using this technique here, this particular equation, and assume cos delta is close to 1 because you are not given cos delta, so you need to use that particular equation if you were to work backwards. The next part of that question, calculate the transformer efficiency for the load condition described. So we have the core loss resistance and the copper loss resistance calculated. So the P copper loss will be the current squared times R. So that's 33.33 squared times 0.08305. That's the copper losses. And the core losses, you can either use whatever value you calculated either on the primary or the secondary. Let's say if you use the secondary volt values, you have 240 squared over the secondary value we calculated was 576. So 576, that's the core losses. This is 92.27 watt, and 240 squared over 576 turns out to be the original no load power loss value anyway. And the total losses is the sum of this. So P total loss is 192.27 watt. And the output power, so it says it's delivering, it supplies a load of 8 kVA at a power factor of 0.8. So the output power will be 8 kVA times 0.8, which is 6,400 watt. This is the output power. So the input power is the output power plus all the losses summed up. So P input power is this plus this, 6,400 plus 192.27 gives you 6,592.57. And then the efficiency is the output power divided by input power. So that turns out to be 6,400 divided by 6,592.57 as a percentage gives you the efficiency, which is 97. Do you have any specific questions on transformer characterization aspects? Yeah. So last question on the three-phase transformers. We have 220 kV kVA 11 kilovolt transformer supplied via a cable with impedance that's given here. That's the cable impedance that's here. And then the transformer impedance referred to the low voltage side is given. So that's the impedance at this point, 3 plus 4J. That's on the secondary side. The load consumes 600 kilowatt. So this particular load consumes 600 kilowatt at lagging power factor of 0.75. And the line-to-line voltage is 11 kilovolts. That's here it's 11 kilovolts and has a 0.75 lagging power factor. Determine the current magnitudes in the windings in the high voltage side and the low voltage side. So if you look at the load, we can write P equals root 3 V line to line, IA, that's the line current here, times cos phi. So the line current in the secondary side will be P divided by root 3 V line to line cos phi, which is the real power is 600 kilowatt, so that's 10 to the power 3, and then root 3, and this particular voltage is at 11 kilovolts, so that's 11 10 to the power 3, and the power factor is 0.75. So this gives you the line current magnitude of line current. So that turns out to be 41.99 amperes, and the low voltage side line current is the same as the winding current as well. It's a star transformer. So here the low voltage side winding current is also 41.99. So now if you consider just one coupled coil here, we have this side rating is 220 and the rating on this side is 11 kilovolt. So the turns ratio is the ratio between 220, let's say A to 1, 220, that's the per phase voltage divided by 11 over root 3, that's the per phase voltage of the secondary side coil. So this turns out to be 220 over 11 is 20, that's the turns ratio. So you have higher current on the low voltage side and lower current on the high voltage side. So effectively the current on the high voltage side has to be lower. So we need to divide this value by 20. So IA will be IA over A. So that's 41.99 over 20. Gives you 2.099. So that's the high voltage winding current, and the line currents are the same. Moving on to the other part, calculate the source line-to-line voltage for the given operating condition. So we have, so although I draw 220 here, that's the rated value, that's the transformer rated value, but then if you have 11 kilovolt and a current conducting here, the voltage here will be not 220, it will be higher. So we need to, we have a cable impedance here and the transformer impedance referred to the low voltage side. So if you remember tutorial 3 or 4, we can either move this to the secondary side or we can move the transformer impedance to the primary side and then lump it up together. So if we move this transformer impedance to the primary side, we can add it with the cable impedance. So then we have a cable impedance and the transformer impedance. And then this side it's 11 kilovolt per phase, and then this side it will be 220 kilovolt per phase voltage, and this will be conducting 2.099 amperes, and then we have to figure out this particular voltage on the primary. So this is the single phase equivalent circuit for this transformer circuit. This is the, so here it's given as 11 kilovolt, so that we can directly relate it to this primary referred secondary voltage as 220 over root 3. So this is already, we know that that's 2500 plus J 3600. This value is the turns ratio squared times the transformer impedance. So the total impedance, I'll write it as Z total, will be 2500 plus J 3600 plus turns ratio squared. So turns ratio is 20 squared 3 plus J 4. That gives you the total transformer impedance. So I'll write it as a phasor, let's say 6382 54.56. So this is the total impedance, both of these combined. So if you find the voltage drop and add it up with this voltage, we have, let's say this is the source voltage, VAN, the source voltage, will be 220 over root 3, this is a kilovolt quantity, plus the voltage drop, that will be 6382 54.456 times 2.099, and then this is feeding at lagging power factor of 0.75, so that will be cos inverse 0.75, which is 41.4. So this is minus 41.4 power factor angle. This is the voltage drop across this total impedance, plus this voltage gives you this voltage here. So this turns out to be 140.094, 1.24 kilovolts. So we are interested in the line-to-line voltage magnitude. So it's this magnitude multiplied by root 3. So VAB magnitude will be root 3 times 140.094. Which will be 242.65. And then last part, determine the power loss in the cable. So we have the current on the high voltage side and the high voltage cable resistance. So this is the resistance 2500. So the power loss will be I squared R. So we have 2.099, that's the current, squared 2500. This is the power loss in one cable. So since it's a three-phase system, we have three such cables. So it will be 3 times this will be the power loss in the cable. Which turns out to be like 33.04 kilowatt power loss in the cable. Yes, yes. Yes, yeah.
There is a whole way. So when they give us the rated value, is it the value here or here?
Rated value. So that's like nominally, let's say if you say this winding is rated at that particular value. Let's say if you excite it at 220 and you don't load it here, you get, let's say for example this one, let's say if you say 220 11 kilovolt rated transformer,
Yeah,
that's,
like
yes, yeah. So then you apply 220 here without any loading, you have 11 kilovolt here.
here.
Yeah, it will be the same. It's no load. Yeah, if there's no load means
like,
yeah.
Like that. So here is 11.
11, and then we neglect this one. So I mean, if you consider the, let's say, no load condition, there's no voltage drop across this one. So let's say if you have the transformer like this, so this, yeah, you can take it. Yeah. So this side, let's say 11 kilovolt, and on this side it will be 220.
Yeah.
But then since there's no current, this side will be 220 anyway.
Because there's no.
Yeah.
Okay, thank you. Thank
That's
you.
the rated values.
So this one will be neglect.
For the rated condition, let's say if you give the rated value, but then if you load it up, then you have a voltage drop across there. Yeah. Yeah.
Thank you.
Yes.
So I want to check, like, how did you find this angle for the current in the plant?
Yes. Yeah. So that's
So is the case going to be similar to that?
yeah, fairly similar.
It's going to be the same.
Not the same.
Different numbers, same questions?
No. Yeah, you can take it. Yes. So here it says 0.75 power
It's called
factor.
inverse cos.
Yeah, inverse cos. Of
Oh,
it.
that's
Yes,
how you
yeah.
want it.
Yeah, so most of the time you get in, I do inverse cos.
But then, isn't this part of the secondary though?
Yeah, lagging power factor so that's related to this
Yeah.
one, and then with respect to this voltage, the current is lagging by power factor 0.75, so this is 11 kilovolt, and then this one is like cos inverse 0.75.
Yeah.
Yeah.
But then this current is in the primary.
Yeah, so this current through this winding and this winding are in phase. So if you have a certain current here, this current will be in phase, just you have to multiply it by the turns ratio.
Oh.
Yeah,
Okay.
it's in phase. It's the
Oh, I
same
see.
phase. Yeah.
All right, thank you.
About this number, the power in, this is the power out plus the power loss. Right?
Yes, yeah.
Yes, also, I have one minus 41.4. Where is that?
That's coming from here. It says 0.75 power factor.
Yep.
So
Just inverse cos.
yes,
by
inverse cos of that.
inverse.
Yes.
So this is
Yeah.
power factor for the secondary.
Yeah, this load here, that's 0.75 power factor, and then this is the voltage, and the power factor. This is I is lagging by cos inverse 0.75. Right.
Also,
What are you guys laughing at?
about the score in total, if I'm able to do all the questions,
Yeah.
how that is counting? Maybe this
You
five,
only have to
five.
get 66% of the answers right to get full marks. Is that right?
Sorry.
So there's 40 marks possible, but it's out of 30. 75%.
Yeah. No, you don't add. We will cut off the highest one. No, I'm joking. We'll cut off the lowest. The lowest one will score. But try to do just 3. Otherwise, I'm not marking, so you can do all 3, all 4. Yeah.
Just try.
Who's marking?
Kazi.
How did you make this test?
Yes. Yeah.
And did you make the one we're doing?
Nope. No, I'm joking. I made it. It's here actually. This is the one. So I'll show it.
Yeah, oh, look over there. There's something going on.
How similar is it to?
It's fairly similar. Yeah, fairly the same concepts, but if you can't by heart it and do it. Probably you need to understand the concepts.
It's
It will
usually
be the
just
same.
numbers changes, and instead of it being capacitive, it might be an RL, for example.
Yes. Yeah. So it's more. You need to know the process.
Yeah, it's the process
Obviously,
part of it. Yeah.
the let's say logic behind your calculation. Then you can do this as well. If you do okay, this one we did v squared over r. So if you do v squared over r in the same, it'll probably not work. You need to figure out whether it's the, let's say I squared over r. Where maybe it's yes, yeah. So things like that.
My issue is more time. In the exam, you get plenty of time, but in the mid-semester and the end of semester, you don't get a lot. It's a bit unfair in a way, but so be it. Because I remember you telling me actually last year that only about 20% actually fully finished the test.
Last year, yes.
I think you were saying about 20-something% we've finished the entire test, every part of it. So it's tough.
You need to get the normal distribution as well. So.
Yeah, you can always be still skewed down at 20%. It's not really.
Question 3 was a bitch.
So effectively what you're saying is you could pick the 3 that you find the least or the most doable and just not
Yeah.
do one.
Use the reading time to do that. Do exactly that.
Yeah.
Choose the one you don't want to do. That's what I do in every exam. I just go, nah, don't want to do it, piss off, and then I'll do the rest.
Is the this lecture?
And do the ones you're most
yes,
strong at in
it's
order
supposed
to,
to be
because
recorded, yes,
it's a good way.
It's green.
Well,
as
it's also to bank time, because then you can focus more time on others,
Yes, yeah.
especially in the exam.
So it's basically, so you have to, let's say you don't care whether it's a delta or a star. So it's, if you have, let's say for example, star, this is,
There won't be any starter delta conversions, will there?
might.
I hate that crap.
So this is this is like a single phase. So this is the per phase voltage, and then line current, and the power of this one it's like V per phase voltage I. So you have 3 such things.
I'm
So
constantly getting confused which equations to use for single phase and which ones to use for 3 phases.
so this one, no, this is per phase voltage times current.
No, but like which
Yeah.
equations to use for which, I'm always getting confused.
So that plus single phase.
This is just one phase. So you'll have 3 such single phases. This is 3 phase power. But then this one, if you look at the voltage line to line, this is the line to line voltage. V line to line, that's like a phasor diagram is like this, VA, VB, VC, and then the line to line voltage is this one, VAB, that's this voltage. It's this one turns out to be √3 times this voltage magnitude. So here you just put in √3 times root 3 times V phase voltage, IA, and then this whole thing we write it as root 3. This thing is the line-to-line voltage and IA. So it's effectively the same. This one is root 3 times line-to-line. This one is 3 times phase.
So if it's line to line, it's always root 3.
Yes. Yeah.
And when is it divided by root 3? Is that
Divided by root 3.
like one of the things is like 415 divided by root 3?
Okay. Yeah. So if you are given this one and then you need to figure out this voltage,
Okay,
then
it's
divide by root 3. Yes. Yeah. If you're just considering, if you want this current and you have this impedance, then you need to do like the current, the phase voltage divided by impedance, for example. But then if you are given line-to-line voltage, then you have to do line voltage divided by root 3.
So I hope it's three phase tomorrow. I've got a feeling because it's the first half, it won't be.
No.
The second half will, but the first half won't. Because the second half is all about three phase.
Yeah.
You mean the induction machines?
And yeah, it's all three phase.
Oh, okay.
Stuff.
No, you have DC machines as well. So.
Oh, just a little bit. But
Yes. Yeah.
I like this. If I feel I slammed the end of the semester and the exam.
don't stress out. I felt the second half was easier than the first half. So if you can get over this hurdle, you might be alright.
Hopefully.
I did feel that the second half was much easier. The transformer stuff was just,
Yeah.
except when we do unbalanced load, that's when you're gonna have some head dramas.
Unbalanced
Are we doing
load.
that in this course still? 'Cause I've noticed we haven't covered that yet.
Oh, you mean the
Unbalanced.
transformer?
Yeah, unbalanced load between the two transformers so that you have to equal them both out, make the changes and then put them back to the way they were again, which is annoying.
That's tutorial 4, right?
No, I don't think we've covered it yet. Unbalanced, I don't think we've covered unbalanced yet. I
Unbalanced.
hope we don't.
So studied the past papers and today, hopefully see how it goes.
Yeah. With my,
Oh yeah. Yes. Yeah.
yeah,
Yeah. It's 12:30, right? 12:30.
yeah,
Yeah,
I've,
yeah.
all that's okay. I can't take the 2:30 anyway because I've got a lab then.
Okay. Or someone's. Is that yours?
Is it? Yes, it is.
Oh, okay.
Thank you. And that's in a different room, isn't it?
Yes.
Yeah. That sheet that I was supposed to let you know by pretty much now,
Oh, the formula.
am I able to
Yeah.
give that to you for you to quickly have a look before the test?
Yeah. That's fine.
That's okay?
Yeah.
It's just I haven't written it yet, I haven't had a chance.
Okay. Yeah.
I've got 3 lab reports all due by the end of this week, so.
Oh, is it?
Yeah. All right, I'll do that tonight and then I'll
Yeah.
give it to you tomorrow.
Yes. Yeah. If you email it me beforehand, then that's better, I guess.
Email it. I'll take a photo and, yeah.
Yeah.
All right. Thanks for that, sir.
Yep. All right.
Come up with something similar or something from the moon?
No, it'll be fairly similar to this one.
Yeah? Are
Yeah.
you sure?
I mean, fairly similar. So
Very similar.
not very.
When any class does like a practice test and stuff, it's usually just number changes and slight variations, that's all it is.
Are you sure?
It's usually.
Let's see tomorrow.
Like instead of being a capacitor, it might be an RL load, for
Are you
example.
going to give us 5 minutes to read?
Yes,
first?
yeah.
Because really, this...
No, yeah, you
So
have
it's-
5 minutes
it's
reading time.
45 minutes test, 5 minutes read.
So this one, it's 40 minutes, right? 40.
Oh my God.
No, 40 minutes writing and then 5 minutes reading. So first 5 minutes you read it.
You only have to do 3 out of 4 questions.
Yeah.
Yeah, but anyway, it's still too long. I need time to process the information.
Use the 5 minutes to work out which one you want to do. Just eliminate it straight away. That way you don't have to think about it and care about it.
Are you sure they're going to be 4 questions?
Yes, yeah.
I already know which one I want to do. I already know. That's what I do in my tests, is reading time, just which one you want to do, and then you work out the order of the ones you want to do. Just do the one you most